check what is this overflow and underflow. In some cases, when we add two numbers, the result exceeds the capacity of the registers. For example, we already assumed 8-bit register. So, we know that the maximum capacity of the number that can be stored in an 8-bit register is equivalent to maximum number in 8-bit register. Okay, this is equivalent to 2 raised to 7 minus 1. This is equal to 127. In our previous class, we learned about this. That means if we add two numbers, its sum is within this 127. Then only our registers can handle that numbers properly. If this addition goes outside this region, this number, then we say that there is an overflow or underflow depending on the situation. Okay, for example, if we add two numbers, that means suppose we want to add 127 plus 2 using 8-bit register. If you don't write any code or any software to do this operation, this gives you wrong result. Why? Because 127 plus 2 in decimal system is equivalent to 129 in decimal system. But your register has only 8-bit capacity. It can store maximum number 127. So this leads to wrong result. So a user should know the capacity of the registers of their microprocessor or microcomputer. If it exceeds the capacity, we have to use some software or code to run the calculation. Okay, this is called overflow or underflow. So, how to understand this overflow occurred or underflow occurred? That is what we want to check next. Okay, for that we can do 3 examples. Okay, 3 or 4 examples. As a first example, we can perform addition of 18 plus 7. All of you know that we are already using 8-bit registers, and 18 plus 7 gives us 25, right? In decimal system it is 25. So this 25 is lies inside this 127, so there is no chance for overflow. Just performing this operation, how to do this? So converting this 18 to its equivalent binary. How to write this equivalent binary? Okay, 16 plus 2. Okay, 16 plus 2. So this is 16, right? Then 1, 0. This is actually 18. Here comes 2. No, like this. 1, 0. Is it right now? 0, 1, 2, 3, 4. Okay. 2 raised to 4, 16. 2 raised to 4, 16. 16 plus 2, 18. Okay. So, this represents 1, 2, 3, 4, 5, 6, 7, 8. 8-bit representation. Okay. So, this represents binary 18. Binary 18. The positional value is written here. I deleted. Okay. Erase that one. So this is the equivalent binary of 18. Then coming to 7. Decimal 7. How to write 7? 7, 4 plus 3. Okay. So 0, 0, 0, 0, 0, 1, 1, 1. 1 plus 2 plus 4, right? 0, 1, 2. 2 raised to 0, 1, 2 raised to 1, 2, 2 2 square 4. 4 plus 3, 7. Okay. So you get here 7. 7 in binary format. Now adding these two. 18 plus 7 gives you 18 plus 7. 0 plus 1, 1. 1 plus 1, 0 with carry 1. 1 plus 1, 0 with carry 1. 0 plus 0 plus carry 1. 1 plus 0, 1. 0, 0, 0. Right? This is the adding this 18 plus 7, you get like this. What is this? In this we can just take its positional values. Here 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. Okay, so its equivalent decimal is 2 raised to 4, 16, plus 2 raised to cube, 8, plus second position no 1, first position no 1, 0th position 1. So you get here like this. What is this? 16 plus 8 plus 1. This is equal to 25. Right? 16 plus 8 plus 1. So you get 25. So 18 plus 7 equal to 25. We have performed the binary equivalence of additions like this. So here you can see that there is no carry into the sign bit. Not the point, this last bit, the most significant bit. This bit is called sign bit. From the right, we move on to left. The last 8 bit is called the most significant bit. This is called the sign bit. Okay, so here there is no carry into the sign bit and no carry out of the sign bit. That is the highlight of this problem. This gives you correct result. There is no error in this calculation. What is the peculiarity? No carry into the sign bit and no carry out of the sign bit. No carry into the sign bit because this is the sign bit. No carry from this to here and no carry from this to outside. So no carry into the sign bit and no carry out of the sign bit. That is the peculiarity of this problem, and here there is no overflow. Remember, in this problem, no overflow or underflow. No overflow. Okay. As a second example, we can perform this addition. Minus 8 plus minus 2. Okay, so already we have done in the earlier problems minus 8. The 2's complement of 8 is called minus 8. Now I don't want to repeat this procedure again. I am just writing minus 8 in its binary form. Minus 8, 1, 1, 1, 1, 1, 0, 0, 0. This is the binary form of minus 8. Similarly, the binary form of minus 2. 1, 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. This is the binary form of minus 2. Now what we want to do? We want to add these two numbers. Okay. So adding these two. 0 plus 0. So I can draw here. Okay. 0 plus 0. 0. 0 plus 1. 1. 0 plus 1. 1. 1 plus 1. 0 with carry 1. 1 plus 1. 0 plus carry 1. 1 with carry 1. 1 plus 1 plus 1 carry 1. 1 plus 1 plus 1 with carry 1. 1 plus 1 plus 1 with carry 1. Okay. So what happens here? There is a lost carry here. So this is equivalent to minus 10 in decimal system. This is equivalent to minus 10 in decimal system. Okay, so there is no overflow or underflow. How to get this minus 10? This is the lost carry. So without this lost carry, you get this is equivalent to minus 10. Okay, since there is a carry which is lost, still you get the correct answer. Here the carry, this last bit, this most significant bit is called the sign bit. Here there is carry into the sign bit. When you add these bits, 1 plus 1, you get 0 with carry 1. So there is a carry into this sign bit, and when you add these sign bits, again a carry out of the sign bit. Do you understand what I said? If you add these bits, from here onwards you get carries up to out of the sign bit. So there is a carry into the sign bit and there is a carry out of the sign bit. Still there is no overflow. So highlight of this problem is that there is a carry into the sign bit, and there is a carry out of the sign bit. There is a carry into the sign bit and there is a carry out of the sign bit. Still you get the correct answer. So we have checked two examples. In the first case, there is no carry into the sign bit and out of the sign bit. The second case, there is carry into the sign bit and out of the sign bit. Still you get the correct answer. As third example, we can add binary equivalence of 127 with 2. Okay, 127 plus 2. So 127 in decimal system is equivalent to 0, 1, 1, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. So this is in the binary. 127 in binary. Now 2. 2 in the decimal system is equivalent to 1 0 in binary. So here there are 6 zeros. Okay, 1, 2, 3, 4, 5, 6, 7, 8. See, this is the binary of 2. Now we want to add these two. Okay, so 1 plus 0, 1, 1 plus 1, 0 with carry 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 1. Then 1, 0 plus 0. So 0 plus 0, 0 plus 1, 1. Okay. There is no lost carry here. You get your result like this. Is this result correct? You have only a bit here 1 0 0 0 0 0 0 1. Is this result correct? You can see that this result is not correct. This is a wrong result. Okay, if you convert this to equivalent decimal, this binary number to its equivalent decimal, this is not equal to 129. But you know that if you add these two in decimal numbers directly, you will get 129. But we add in we have used 8 bits here. Because we already know that this 8-bit register has maximum storage capacity of 127. We have our result as 129. Okay, so in this case, here an underflow happens. Why it is called underflow? Because in this case, you can see that if you add these numbers, when it comes to here, you have a carry into the sign bit, but there is no carry out of the sign bit. So in this problem, there is carry into the sign bit. There is carry into the sign bit, but no carry out of the sign bit. Out of the sign bit. There is a carry into the sign bit, because if you add here 1 plus 0, here 1 plus 1 plus 0, 0 is carry 1. Here comes a 1. But there is no carry out of the sign bit. There is a mismatch of carry here. A carry into the sign bit, but no carry out of the sign bit. Here there is an underflow. There happens underflow. So you get wrong result when we add binary numbers together. As our fourth example, we add these two numbers, minus 92 plus minus 64. Okay, 92 plus 64. So in that case, minus 92 is equivalent to binary of this, and minus 64 is equivalent to binary of this. Now we want to add these two numbers. When you add these two numbers, 0 plus 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1, 0 with carry 1. There is a lost carry. Okay, so what happens here? Here, when you add these two numbers, you get this output like this. But this is not equal to, when you add these two, what you get? Minus 2, 6, minus 156, right? But when you convert these two, it's equivalent binary. This is not equal to minus 156. What happened to this problem? In this problem, there is no carry into the sign bit, but there is a carry out of the sign bit. So, here what happens? The highlight of this problem is, no carry into the sign bit, but there is a carry out of the sign bit. There is a carry out of the sign bit. Okay, so this is an example for overflow. In this case, there is no carry into the sign bit, but there is a carry out of the sign bit. So these examples gives us the chances for overflow or underflow. Here all we can see that when there is a mismatch in the carry to the sign bit, there is overflow or underflow. So if you get a correct answer, there should be a match. If there is a carry into the bit, there should be a carry out of the bit. If there is no carry into the sign bit, there should be no carry out of the sign bit. If there is a mismatch in this case, there happens overflow or underflow. Okay, so I hope that you can understand binary arithmetic. In this section, we added two binary numbers. We learned the rules for binary addition and binary subtraction. In order to subtract a number, we have to add the 2's complement of the number being subtracted. That is the rule. In all these problems, we assume 2's complement representation for negative numbers. So, you learn well and do so many problems as you could and understand the method how to perform this binary arithmetic.